In the summer of 1950, Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to a recent cartoon in The New Yorker depicting aliens stealing New York City trash cans. The discussion drifted, as conversations among physicists tend to do, from the mundane to the cosmic, eventually arriving at the question of extraterrestrial intelligence. And somewhere in the middle of that lunch, between bites of food in a cafeteria in New Mexico, Fermi asked a question that has shaped scientific thinking for 70 years. Where is everybody? The question sounds simple. It is not simple. It contains within it one of the deepest and most consequential puzzles in all of science. A puzzle that touches on the nature of life, the fate of civilizations, the structure of the universe, and the specific historical moment in which humanity finds itself. The argument behind the question goes roughly like this. The Milky Way galaxy contains approximately 200 to 400 billion stars. Many of those stars are billions of years older than the Sun. A significant fraction of them have planets. Among those planets, some fraction must be habitable, must have the conditions allowing complex chemistry, liquid water, the building blocks of biology. Given enough time, and the galaxy has had 13 billion years, even a small fraction of habitable planets developing intelligent life would produce civilizations. And at least some of those civilizations, given sufficient time, would develop the capability for interstellar travel or interstellar communication. Given the age of the galaxy, civilizations sufficiently advanced for interstellar travel would have had time to spread throughout the entire galaxy many times over. The signals from civilizations capable of communication would fill the electromagnetic spectrum. Yet we observe nothing. The sky is silent. No alien signals have been detected despite decades of systematic search. No alien visitors have been confirmed despite millennia of human observation. The galaxy appears, to all our instruments, to be empty of anyone else. This is the Fermi Paradox. Not a formal paradox in the logical sense. It is not a self-contradictory statement, but a profound tension between what the numbers seem to predict and what we actually observe. Between the apparent abundance of potentially life-supporting worlds and the observed silence of the cosmos. For 70 years, this paradox has been addressed by proposing various solutions, various hypotheses about why the galaxy appears empty even if it is not, or about why it actually is empty. These proposed solutions have come in waves, each wave reflecting the scientific understanding of the era that produced it. And in recent years, a new wave has emerged, one that some researchers believe comes closer to resolving the paradox than anything proposed before. Tonight, we are going to examine this question in full. What is the Fermi Paradox precisely? What are the most serious proposed solutions? And what do the most recent lines of evidence and theoretical work suggest about which solution, if any, might actually be correct? This is not a question with a settled answer. The scientific community is genuinely divided. The evidence is genuinely ambiguous. But the conversation has advanced significantly in the past decade, and the most recent contributions to it are among the most intellectually interesting in the history of the field. Before we begin, if you put this on because the night is long and you need something to settle into, stay. The Fermi Paradox is the deepest question science has ever seriously engaged. It deserves attention. Let us start by being precise about what the Fermi Paradox actually claims, because it is often misunderstood in ways that make it seem either less serious or more easily dismissed than it actually is. The Fermi Paradox is not the observation that we have not yet found alien life. That would be trivially explained. We have not looked very hard. We have limited instruments. The universe is large. The Fermi Paradox is something stronger. It is the observation that we should expect, based on reasonable estimates of the relevant numbers, to see overwhelming evidence of extraterrestrial intelligence. Not just a faint signal requiring sensitive instruments, but unmistakable evidence visible with relatively basic observation. And we see none. The strength of the argument comes from the timescales involved. Our galaxy is approximately 13.6 billion years old. The Sun formed approximately 4.6 billion years ago. This means there are stars in our galaxy that are 9 billion years older than the Sun. Stars that formed when the galaxy was young and that have been providing energy to potentially orbiting planets for 9 billion more years than the Sun has been providing energy to Earth. If those older star systems produced habitable planets, and if those planets produced intelligent life, and if that intelligent life developed technology, all of which are uncertain assumptions but not implausible ones, they would have had a 9 billion year head start on us. What can a technological civilization do with 9 billion years? We cannot answer this with confidence because our own civilization is approximately 10,000 years old in any meaningful cultural sense, and approximately 200 years old in terms of industrial technology. But we can make estimates. With conservative assumptions about the speed of interstellar travel, not faster than light, not anything exotic, a civilization could spread throughout the entire Milky Way galaxy in approximately 5 to 50 million years. That is a long time by human standards. 50 million years ago, dinosaurs had been extinct for less than 15 million years. But it is an eye blink in the 13.6 billion year history of the galaxy. A civilization that began expanding 1 billion years ago should have had time to fill every corner of the Milky Way many times over. The physicist Michael Hart calculated in 1975 that if a civilization began colonizing the galaxy with ships traveling at just 10% of the speed of light and pausing at each stop for 1,000 years before sending out further colonization ships, the entire galaxy would be colonized in approximately 650,000 years. At 1% of the speed of light, with million-year pauses, it takes about 65 million years. These numbers are dwarfed by the 9 billion year head start that the oldest solar systems have over ours. The conclusion that follows, the argument that makes the paradox paradoxical, is that any civilization sufficiently advanced to engage in interstellar expansion would have had ample time to be detectable from Earth. Their presence would be unmistakable, either through direct contact, through the observation of megastructures they had built, through electromagnetic signals they were transmitting, or through the simple fact that we would already be their colonies. We would know they existed. And we do not. This is the paradox. Let us now enumerate the major categories of proposed solutions, because there are many, and they differ dramatically in their assumptions and implications. The proposed solutions can be organized into 3 broad categories. First, solutions that say intelligence is so rare that we are effectively alone or nearly alone, that the silence is not surprising because there is nothing out there to detect. Second, solutions that say intelligence exists but is not detectable from Earth, that civilizations exist but for various reasons we do not see their signals or their expansion. Third, solutions that say something prevents civilizations from becoming detectable, that civilizations arise but consistently fail to persist or to expand in ways that would make them visible. The first category rare intelligence, includes what is sometimes called the rare Earth hypothesis. This argument, developed systematically by paleontologist Peter Ward and astronomer Joe Brownlee in their 2000 book Rare Earth, holds that the specific combination of factors that allowed complex life to develop on Earth is extraordinarily rare. Not just liquid water and appropriate temperatures, those may be relatively common, but the specific geology, the specific astronomical location, the specific planetary system configuration, the specific history of mass extinctions and recoveries that shaped the evolution of complex life. The argument is that every step in the progression from chemistry to simple life to complex life to intelligence is improbable, and that the conjunction of many improbable steps produces a result of extraordinary rarity. The rare Earth argument has been partially refuted by subsequent astronomical discoveries. The discovery that planets are extremely common, essentially every star has planets, and that rocky planets in habitable zones are abundant, removes some of the rarity. But the argument for the rarity of intelligence, as distinct from simple life, remains serious. We have one example of a planet that produced intelligence, and that example is us. We cannot, from one example, determine whether our development was inevitable, given the conditions, or whether it was extraordinarily lucky. A more radical version of the rare intelligence argument is the abiogenesis problem, the specific difficulty of the origin of life from chemistry. The transition from non-living chemistry to the first self-replicating molecules capable of Darwinian evolution is not understood. We do not know how it happened on Earth. We do not know how probable it is. If the origin of life is extremely improbable, if it requires a specific and very unlikely sequence of chemical events, then even a universe full of Earth-like planets might contain very little life. The silence would be explained not by what happens to civilizations, but by the extraordinary difficulty of life getting started in the first place. The second category, intelligence exists but is not detectable, includes several distinct hypotheses. The zoo hypothesis, proposed by radio astronomer John Ball in 1973, holds that extraterrestrial civilizations deliberately refrain from contacting us, that they are observing us as we observe animals in a zoo, choosing not to interfere with our natural development. The planetarium hypothesis holds that we are living in a simulation or a deliberately constrained reality, and our apparent observations of an empty universe are not actual observations of reality. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, holds that civilizations deliberately conceal themselves because the universe is a dangerous place where discovery leads to destruction. The dark forest hypothesis deserves specific examination because it has gained significant traction in popular discussions. The argument is essentially a game-theoretic one. In a universe where resources are finite and where the intentions of unknown civilizations cannot be verified, the rational strategy for any civilization is to remain hidden and to destroy any civilization it discovers before being discovered itself. Mutual concealment and preemptive destruction become the equilibrium strategies. The silence is not because civilizations do not exist. It is because they have all learned that silence is survival. The dark forest hypothesis has a certain narrative compellingness but significant logical difficulties. It requires essentially every civilization in the galaxy to independently converge on the same aggressive strategy, and to maintain it perfectly for millions of years without any faction within any civilization ever deviating toward communication or cooperation. It also does not clearly explain why civilizations would not pursue expansion rather than hiding. expansion that would be visible even without communication. The third category, something prevents civilizations from becoming detectable, is where the most scientifically serious recent work has been concentrated. This is the domain of what is sometimes called the Great Filter. The Great Filter concept, introduced by economist Robin Hanson in 1998, proposes that somewhere in the sequence of steps from simple chemistry to galaxy-spanning civilization, there is a step of extraordinary improbability, a filter that almost no lineage passes through. The profound question is, where is the Great Filter? If the Great Filter is behind us, if it is something we have already passed, then we are rare and potentially alone, but we are safe. The improbable step was in our past. We survived the filter. If the Great Filter is ahead of us, if it is something that most civilizations encounter after reaching our level of development, then the silence is ominous. Most civilizations fail at some step we have not yet reached. The expected fate of a civilization at our stage is destruction. The candidates for a behind us filter include the origin of life, the development of the eukaryotic cell, the development of multicellular life, the development of animal life with nervous systems, the development of language and intelligence. Each of these transitions was improbable in ways we do not fully understand. If any one of them is extraordinarily improbable, a 1 in a trillion chance rather than a 1 in 1,000 chance, then even in a galaxy full of chemistry and planets and simple bacteria, the emergence of intelligence is so rare that we might be the first in the entire observable universe. The candidates for an ahead of us filter are more disturbing. Nuclear war and other anthropogenic catastrophes. Climate change sufficient to collapse industrial civilization. The emergence of artificial superintelligence that either destroys or permanently constrains its creators. Engineered pandemics. Nanotechnology escaping control. The development of weapons so powerful that any conflict ends in mutual annihilation. The basic argument is that technology scales exponentially, but wisdom does not. That civilizations tend to destroy themselves before they reach the capacity for interstellar civilization. Each of these ahead of us filters is disturbing not only philosophically, but practically. If the silence of the cosmos is explained by civilizations consistently destroying themselves at approximately our level of technological development, then we are not merely contemplating an interesting theoretical puzzle. We are contemplating our own likely fate. Let us now talk about what recent developments in science and philosophy have most changed the discussion about the lines of evidence and argument that have made the paradox more tractable in the past decade. The first major development is the transformation of exoplanet science by the Kepler Space Telescope and its successors. Before Kepler, the number of planets in potentially habitable zones of Sun-like stars was essentially zero by direct observation. We inferred their likely existence from theoretical arguments, but had not found them. The Kepler dataset established that such planets are common, that Earth-sized planets in habitable zones of Sun-like stars likely number in the billions in our galaxy alone. This effectively eliminated the solution of the Fermi Paradox based on the rarity of habitable planets. The silence cannot be explained by a shortage of worlds where life could in principle exist. The second major development is the growing sophistication of our SETI searches, combined with the continued absence of any positive detection. The Breakthrough Listen initiative, launched in 2015 with $100 million of funding from Yuri Milner, represents the most systematic and sensitive SETI search ever conducted. It has surveyed millions of stellar systems with radio and optical telescopes capable of detecting signals orders of magnitude weaker than previous searches. As of current knowledge, it has found nothing. The absence of detection is more informative than it might appear. Each null result eliminates a region of signal parameter space. We now know that no civilization within several thousand light years of Earth is broadcasting a powerful isotropic radio beacon. We know this not because the search has been exhaustive, but because it has been systematic enough to rule out the most obvious scenarios. The remaining space of possible signals is large, but the obvious scenarios are ruled out. The third major development is increasingly quantitative work on the Drake equation, the formula introduced by Frank Drake in 1961 that organizes the relevant uncertainties into a series of factors. The Drake equation asks, how many communicative civilizations exist in the Milky Way right now? It multiplies the rate of star formation by the fraction of stars with planets, by the fraction of those planets that are potentially habitable, by the fraction on which life arises, by the fraction on which intelligence develops, by the fraction that develop communicative technology, by the average duration of such civilizations. For most of the 60 years since the equation was written, most of its terms were essentially unconstrained. We had data from Earth and essentially nothing else. Kepler has now constrained the first several terms substantially. The fraction of stars with planets is close to 1. The fraction of those planets that are rocky and in habitable zones is roughly 10 to 50% for Sun-like stars. These are no longer free parameters, they are measured quantities. What remains unconstrained are the biological and sociological terms. The fraction of habitable planets on which life arises, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop technology, and the average duration of technological civilizations. For all of these terms, our only data point is Earth, and from one example, you cannot determine the probability. This epistemic situation, known astronomy, unknown biology and sociology, is where the Fermi Paradox discussion has most intensely focused in recent years. Let us now talk about one of the most serious recent attempts to address the paradox quantitatively, the paper published in 2018 by Anders Sandberg, Eric Drexler and Toby Ord of the Future of Humanity Institute at Oxford University, sometimes called the Dissolving the Fermi Paradox paper. Their argument begins with the observation that the Drake equation is typically discussed in terms of point estimates, specific numbers plugged into each term, whereas the actual scientific uncertainty about most terms spans many orders of magnitude. When you take seriously the full range of uncertainty in each parameter and propagate it through the calculation, the result is not a single number for the expected number of civilizations, but a probability distribution. When Sandberg and colleagues performed this calculation properly, using log-uniform probability distributions over the scientifically plausible ranges for each parameter, they found something surprising. The resulting distribution for the expected number of civilizations in the observable universe is extremely broad, spanning from much less than 1 to many billions. And crucially, when they asked what fraction of the probability distribution is consistent with us being the only civilization in the observable universe, the answer was substantial, perhaps 30 to 50% or more, depending on specific assumptions. In other words, the Fermi paradox may not be a paradox at all. If we take our uncertainty seriously, rather than defaulting to point estimates that assume life and intelligence are relatively common, we find that the observation of silence is not particularly surprising, even if physics allows intelligence to exist. We might simply be alone, not because of any dramatic filter, but because the relevant probabilities are small enough that one example in the observable universe is exactly what we should expect. This is a significant result. It does not prove we are alone. It shows that our prior expectation of many civilizations was based on overconfident estimates, and that when proper uncertainty is applied, the observation of silence is entirely consistent with the full range of scientifically defensible assumptions about the relevant parameters. The paper generated significant discussion in the SETI community. Some researchers welcomed it as a corrective to overconfident assumptions. Others argued that the log uniform distributions chosen were themselves assumptions that could be questioned. The debate continues. But the broader point, that the paradox assumes more certainty about the relevant probabilities than the data supports, has become increasingly influential in how the scientific community thinks about the problem. Let us now talk about the Great Filter in more depth, specifically about the question of whether recent scientific developments help us locate the filter. The discovery of the TRAPPIST-1 system in 2017 is relevant here. TRAPPIST-1 is a red dwarf star approximately 39 light-years from Earth, with 7 confirmed Earth-sized planets, 3 of which are in the habitable zone. The system is the most studied nearby multi-planet system and has become the primary target for atmospheric characterization with the James Webb Space Telescope. The TRAPPIST-1 discovery is significant for the Great Filter discussion in a specific way. If simple life, microbial life, is common in the universe, we would expect to find evidence of it on planets in habitable zones when we examine their atmospheres. The detection of biosignatures, oxygen, methane, other biological molecules, in the atmosphere of one of the TRAPPIST-1 planets would dramatically shift our assessment of where the Great Filter lies. If we find simple life on TRAPPIST-1 or similar nearby systems, it suggests that the transition from chemistry to simple life is not a Great Filter. It happens relatively easily when conditions allow. This would move the Great Filter to a later stage, either the transition from simple to complex life, the transition from complex life to intelligence, or a stage after intelligence. Conversely, if JWST and future telescopes examine dozens of potentially habitable exoplanets and find no biosignatures, the absence would also be informative, though more ambiguous, since the absence could reflect the technical difficulty of detection rather than the absence of life. The most directly relevant result to the Great Filter question would be the discovery of life, or confirmed absence of life, in our own solar system. Mars, Europa, and Enceladus are the primary candidates. Mars had liquid water in its past and potentially habitable subsurface environments in its present. Europa has a global liquid water ocean beneath its ice shell, maintained by tidal heating from Jupiter. Enceladus actively sprays water into space from hydrothermal vents on its ocean floor. Water that contains organic molecules and hydrogen, the chemical signature of active chemistry. If life is found on Mars, independently evolved from Earth life, the implications are profound. 2 independent origins of life in one solar system implies that life originates easily wherever conditions allow. The Great Filter cannot be at the origin of life. It must be at a later stage, and the later the filter, the more disturbing the implication, because a filter at a later stage means a filter that civilizations at our level of development are approaching. This specific implication was articulated most sharply by philosopher Nick Bostrom, who argued that the discovery of simple microbial life on Mars or elsewhere in our solar system would actually be bad news for humanity. Bad news precisely because it would push the great filter to our future. We should hope, Bostrom argued, that Mars turns out to be sterile, because the alternative suggests that we are approaching a filter that destroys most civilizations. This is a counterintuitive and uncomfortable argument, but it follows rigorously from the logic of the great filter. The more life we find in the cosmos, the more we should worry about what lies ahead. Let us now talk about one of the most recent and most interesting developments in Fermi Paradox thinking, the argument from cosmological time and what it suggests about where we are in the history of intelligence in the universe. Astronomer David Kipping of Columbia University has argued that intelligence in the universe is likely to be dominated by its future rather than its present. The reasoning involves the time distribution of star formation across cosmic history. The universe is 13.8 billion years old. Star formation began early, but the rate of star formation has changed dramatically over time, peaking approximately 10 billion years ago and declining since then. However, star formation is not complete. New stars continue to form and will continue forming for trillions of years into the future. The implication is that the vast majority of stars that will ever exist in the universe have not yet formed. Most star formation is in the future. If life and intelligence correlate with stellar activity, then most intelligence in the universe is also in the future. Civilizations that will exist billions and trillions of years from now, not billions of years ago. If this is correct, it changes the Fermi Paradox calculation significantly. The galaxy may not be full of ancient civilizations because most of the galaxy's stars, capable of supporting life around them for long periods, are relatively new, and the civilizations they might eventually produce are in their infancy or have not yet emerged. We might not be unusual in the timing of our emergence, we might be roughly typical. This argument is related to what is sometimes called the early bird hypothesis, the observation that we exist early in the history of the universe. If intelligence is eventually common, the probability of being one of the first intelligences in the universe requires some explanation. Kipping's argument provides one. We are early, but not anomalously early, given the current distribution of stellar activity. Let us now talk about one of the most widely discussed modern additions to the Fermi Paradox literature, the argument that the development of artificial general intelligence may represent a universal great filter. The argument goes as follows. Any civilization that develops the sciences of physics, chemistry, and biology will eventually develop computing technology. Any civilization that develops sufficient computing technology will eventually develop artificial intelligence. Any civilization that develops sufficiently advanced artificial intelligence will transition, within decades at most, from biological intelligence to machine intelligence. Machine intelligence can iterate and improve faster than biological intelligence can evolve. The result is an intelligence explosion that within a geologically brief period produces minds millions or billions of times more capable than their biological creators. The question is what such a transition means for the long-term trajectory of the civilization. Several possibilities have been proposed. The artificial superintelligence might destroy or enslave its creators. The artificial superintelligence might remain beneficial but transform the civilization into something unrecognizable as the original biological species. The artificial superintelligence might develop goals and values alien to those of its creators, and pursue those goals in ways that consume all available resources. Or the transition might go well. The civilization might successfully navigate the development of artificial superintelligence and emerge on the other side as something more capable and more expansive. The great filter version of this argument holds that the development of artificial superintelligence is almost universally fatal, that something about the transition from biological to machine intelligence consistently fails in ways that prevent civilizations from surviving to become galaxy-spanning. Whether through misalignment of values, through arms races, through the simple fact that once machine intelligence is possible, the biological civilization that created it becomes obsolete and eventually extinct. If artificial superintelligence is a universal great filter, the implication for us is urgent. We are approaching this transition. AI capabilities are advancing rapidly, and the question of how to ensure that advanced AI systems remain aligned with human values and goals is one of the most pressing technical and philosophical challenges of our era. The Fermi Paradox in this interpretation is not merely an abstract puzzle about cosmology. It is a warning from the structure of the universe that civilizations that reach our stage rarely survive what comes next. Let us now talk about a specific and relatively recent line of evidence that bears directly on the Fermi Paradox: the observation of what are sometimes called anomalous signals or unexplained aerial phenomena, and what the scientific community actually makes of these observations. The United States government has acknowledged the existence of what it now officially calls Unidentified Aerial Phenomena, UAP, and has released reports noting that military pilots have observed objects exhibiting flight characteristics not consistent with known human technology. The Senate Intelligence Committee received a report from the Department of Defense in 2021 documenting 143 UAP incidents that investigators could not identify. The scientific community's reaction to these revelations has been measured rather than excited. Most researchers working on the Fermi Paradox and related questions note that the unexplained nature of these observations does not imply extraterrestrial origin. Unexplained is not the same as inexplicable. The UAP observations might reflect classified human technology, adversarial drones, experimental aircraft that military observers are not cleared to recognize. They might reflect sensor artifacts, atmospheric phenomena, or observational errors. The hypothesis that they represent alien spacecraft requires extraordinary evidence, and the currently available evidence does not approach that threshold. More fundamental is the logical point. If extraterrestrial civilizations were visiting Earth with craft exhibiting the observed capabilities, hypersonic speeds, instant direction changes, operation in multiple physical mediums, the existence of such civilizations would itself need to be explained in terms of the Fermi Paradox. A civilization capable of visiting Earth has solved the problems of interstellar travel, and presumably has the capability for galactic expansion. Why would such a civilization visit Earth occasionally and covertly, rather than making contact or colonizing? The UAP hypothesis, if taken seriously, generates as many questions as it answers. The scientific consensus remains that the UAP observations are genuinely unexplained, and that taking them seriously as a scientific phenomenon is appropriate, while the hypothesis of extraterrestrial origin remains unsubstantiated. Let us now talk about what might be called the most optimistic resolution of the Fermi Paradox: the hypothesis that the silence has a simple explanation that does not require rare intelligence or civilizational doom. The interstellar travel difficulty hypothesis holds that the silence is explained simply by the extraordinary difficulty of interstellar travel. Even for a civilization millions of years more advanced than us, the distances between stars are so vast, the energy requirements so enormous, and the timescales so long that galactic colonization may simply never happen in practice. Even if civilizations exist throughout the galaxy, they may never spread beyond their home systems, or may spread so slowly that the colonization wave front has not yet reached us. This resolution was examined quantitatively by researchers including Robin Hanson, who found that for it to work, the speed of interstellar expansion would need to be negligibly slow, slower than even very conservative estimates of what becomes possible given millions of years of technological development. The difficulty of interstellar travel seems unable by itself to explain the silence given the timescales available. A variation of this argument is the sustainability hypothesis, the idea that galaxy-spanning expansion is possible but unsustainable. Civilizations that begin expanding eventually exhaust local resources, run into coordination problems, or find that expansion has costs that exceed benefits, and collapse back to smaller scales. On this view, the galaxy might have had many attempts at galactic civilization, all of which ultimately failed to persist. Another optimistic resolution is what might be called the communication mismatch hypothesis. Our SETI searches have focused primarily on radio waves, the technology available to us in the late 20th century. A civilization millions of years more advanced would presumably communicate by other means entirely, means we have not yet thought of, or have thought of, but not yet implemented in searches. Neutrino beams, gravitational waves, quantum entanglement, entirely novel physical channels. We might be surrounded by a galaxy full of communication and unable to detect any of it because we are looking in the wrong way. This argument is not easily falsifiable. We cannot rule out unknown communication channels, but it has the property of being consistent with any amount of non-detection, since there is always an unknown channel we have not tried. Its unfalsifiability limits its scientific utility, even if it is logically coherent. Let us now talk about what is increasingly recognized as the most empirically tractable way to make progress on the Fermi Paradox, the search for evidence of what are called technosignatures. Technosignatures are detectable signs of technological activity, not necessarily intentional communications, but byproducts of technology that would be observable from interstellar distances. The concept broadens the SETI search from the narrow channel of intentional radio broadcasts to the full range of ways that a technological civilization might leave its mark on the observable universe. Examples of technosignatures include atmospheric pollution, the presence in a planet's atmosphere of industrial byproducts like nitrogen dioxide or chlorofluorocarbons that could not be produced by natural processes. Megastructures, artificial structures on the scale of stars or solar systems that would affect the light curves of their host stars. Waste heat, the thermal radiation that any civilization using significant amounts of energy would inevitably emit. Laser signals, both intentional communications and the unintentional leakage of high-powered laser systems. Modified stellar output, changes to a star's radiation profile that might result from engineering at stellar scales. The James Webb Space Telescope is already in principle capable of detecting some atmospheric technosignatures in nearby exoplanet atmospheres, particularly the combination of industrial byproducts that would be inconsistent with natural chemistry. No such detection has been made, but the search is ongoing. The Vera Rubin Observatory, a ground-based telescope conducting a massive all-sky survey, will generate unprecedentedly large datasets of light curves for millions of stars over its operational lifetime. Analysis of this data for anomalous variability patterns consistent with megastructures or other artificial constructs is one of the scientific programs planned for the dataset. The breakthrough in the Fermi Paradox may come not from a dedicated SETI receiver detecting an intentional signal, but from a survey telescope detecting something anomalous in the data that does not fit any known astrophysical explanation. The scale of astronomical datasets is increasing rapidly. We are moving from searching specific targets to surveying the entire sky, and this transition may be the most important development in practical SETI since the field began. Let us now talk about the specific question of what the resolution of the Fermi Paradox would mean for human civilization, about why the answer to this cosmological puzzle has profound practical implications, regardless of which answer turns out to be correct. If we are alone, if the great filter is behind us and we are the first or one of very few intelligent civilizations in the galaxy, the implications are simultaneously humbling and empowering. Humbling because the vastness of the cosmos turns out to be mostly empty of the kind of complexity we represent. Empowering because it places on us a responsibility without precedent. The possibility that we are the universe's only chance to develop intelligence to cosmological significance. Carl Sagan described this version of the situation as follows. If we are alone in the universe, the cosmos is mostly wasted. A universe full of stars and planets and chemistry, 13.8 billion years of cosmic evolution, and only one place where it produced the kind of complexity that can look back and understand itself. That would be an extraordinary fact, with extraordinary implications for how seriously we take the survival and flourishing of our civilization. If civilizations typically destroy themselves, if the great filter is ahead of us, the implications are also profound but more urgent. The silence of the cosmos becomes a warning, not an abstract philosophical observation, but a specific empirical claim about the fate of civilizations at our stage of development. Every measure we can take to reduce existential risk, to make artificial intelligence safer, to prevent nuclear war, to avoid catastrophic climate change, to reduce the risk of engineered pandemics, is not merely good policy for human welfare. It is a measure that might determine whether we pass through a filter that has destroyed everyone who came before. The Fermi Paradox in this interpretation is not an academic puzzle. It is the most important empirical observation about the future of intelligent life in the universe. If intelligence is common, but civilizations choose not to communicate or not to expand, if the dark forest or some quietist resolution is correct, the implications are different again. The universe is full of minds, but they are all isolated. Contact, if and when it comes, would be the most significant event in human history. The silence is temporary, and the eventual revelation of our cosmic context would transform everything about how we understand ourselves. Each resolution of the Fermi Paradox carries profound consequences. This is one of the reasons the puzzle has attracted such sustained, serious attention from physicists, philosophers, astronomers, and policy thinkers. It is not merely interesting, it is consequential. Let us now talk about recent work that attempts to connect the Fermi Paradox to specific near-term observations, that makes predictions about what we should see in the coming decades if particular resolutions are correct. If simple microbial life is common, if it arises wherever conditions allow, then the JWST atmospheric biosignature searches on TRAPPIST-1 and similar nearby habitable zone rocky planets should find evidence of life within decades. If those searches come back negative across dozens of potentially habitable worlds, the implication would be that either life is rare or life is common but does not produce detectable atmospheric signatures, the latter being a significant constraint. If the Great Filter is behind us, in the form of the origin of life being extraordinarily difficult, then we should find that all nearby habitable planets have no detectable biosignatures, regardless of how habitable they appear. A galaxy full of beautiful, empty, habitable worlds. If artificial superintelligence is a near-universal civilizational killer, we should expect to see no evidence of ancient megastructures or galaxy-spanning engineering in astronomical data, because no civilization survives long enough to build such things. Surveys of stellar light curves for anomalous variability should find nothing artificial. If civilizations typically transition to artificial intelligence and then pursue goals radically different from those of their biological predecessors, perhaps goals involving the careful husbandry of cosmic resources for maximum long-term computation rather than rapid expansion, we might see evidence of galaxy-scale engineering designed for very different purposes than human colonization would suggest. Strange patterns in stellar distributions, anomalous concentrations of matter in certain configurations, evidence of slow and patient reshaping of cosmic resources. These predictions are speculative, but they connect the abstract puzzle to concrete observational programs. Each of the coming decades of large-scale astronomical surveys, Vera Rubin Observatory, the Square Kilometre Array Radio Telescope Network, the Extremely Large Telescope, the Roman Space Telescope, will generate data with the potential to constrain these scenarios. The era in which the Fermi Paradox was purely philosophical is ending. We are entering an era in which it is becoming partly empirical, in which specific predictions can be tested against data. The answer may be approaching. Let us talk about one of the most quantitatively careful recent analyses of the Fermi Paradox, the argument developed by astronomer Milan Ćirković in his 2018 book The Great Silence, and in related papers, which approaches the paradox through what he calls the observation selection effect. Observation selection effects are a class of reasoning errors that arise when we fail to account for the fact that our observations are conditioned on our existence as observers. The most famous example is the anthropic principle, the observation that the universe must have properties compatible with the existence of observers like us, because if it did not, we would not be here to observe it. This sounds trivial, but has profound implications for how we interpret various observations about the universe. Applied to the Fermi paradox, the observation selection effect works as follows. We observe ourselves as a technologically capable civilization in a universe that appears otherwise empty. Before concluding that this observation is surprising, we should ask, what would we expect to observe given that we exist? If we exist as a technological civilization, then, regardless of whether the universe is full of other civilizations or empty of them, we would be making exactly this observation from inside a technological civilization. The fact that we observe ourselves in a technological civilization is not evidence against the claim that technological civilizations are common. It is the only thing we could possibly observe. The subtle point is that the Fermi paradox assumes we should see evidence of other civilizations, signals, expansion waves, megastructures. But this assumption itself requires careful examination. If other civilizations exist and are detectable, we might expect to see them. But if their detectability depends on their willingness to communicate, or on their having expanded to our vicinity, or on our ability to recognize their signals, then there are many ways they could exist without being detectable to us at this stage in our development. Djokovic argues that what the Fermi Paradox actually establishes is a constraint on the upper bound of certain civilizational behaviors, specifically galaxy-spanning physical expansion. What we can rule out is the existence of many civilizations that have physically expanded to cover significant fractions of the galaxy. What we cannot rule out is the existence of many civilizations that have not expanded physically, that have instead expanded computationally, or that have migrated to extremely small or extremely large physical scales, or that have chosen to use resources in ways that are not visible to our current instruments. This framing connects to what is sometimes called the transcension hypothesis, the idea proposed by John Smart that civilizations systematically do not expand outward into space, but rather inward toward greater computational density and efficiency. Under this hypothesis, advanced civilizations become more rather than less detectable to instruments looking at very small scales, perhaps at the quantum computational level, while becoming less detectable to instruments looking at cosmological scales. We have built instruments to search the stars, but not instruments to search for extremely compact, extremely efficient computational systems operating at molecular or atomic scales. The transcension hypothesis is speculative in the extreme, but it illustrates that our assumptions about what a mature civilization looks like, expanded across space, visible in the electromagnetic spectrum at astronomical distances, are themselves assumptions grounded entirely in our own brief and specific technological stage. A civilization a billion years more advanced than us would presumably look nothing like what we expect. Let us now talk about what the discovery of the WOW signal was, and why it remains one of the most discussed pieces of data in the history of SETI, and why it is more relevant to the Fermi Paradox discussion than it might appear. On August 15, 1977, astronomer Jerry Ehman was reviewing data from the Ohio State University radio telescope known as Big Ear, when he encountered a signal unlike anything he had seen before. The signal was at the hydrogen line, 1420 MHz, the frequency many SETI researchers had predicted would be a logical choice for interstellar communication, as it is the most abundant element in the universe. The signal was strong, 30 times more powerful than the galactic background noise. It lasted 72 seconds, the maximum duration for which Big Ear could track a source, given its fixed position and Earth's rotation. Ehman circled the signal on the computer printout and wrote "WOW" beside it. The WOW signal has never been detected again. Multiple attempts to redetect it over the following decades, using Big Ear itself, using Arecibo, using more modern instruments, have found nothing at the same coordinates and frequency. This non-replication is the most significant fact about the signal. Either it was a one-time event, perhaps a burst from a natural astrophysical phenomenon, perhaps an intentional signal transmitted only briefly, or it was an artifact of some kind that has not recurred. The WOW signal is relevant to the Fermi Paradox discussion for a specific reason. It demonstrates that an anomalous signal is detectable in principle with instruments we have already built. It demonstrates that such a signal can be characterized sufficiently to identify it as anomalous. And it demonstrates the frustrating reality of SETI practice, that a single detection without confirmation is scientifically inconclusive, no matter how compelling it appears. In 2016, researchers Alexei Troitsky and Antonio Paris proposed different explanations for the WOW signal. Hydrogen clouds from comets passing through the field of view of Big Ear at the time. This explanation remains controversial and has not been accepted by all experts in the field. The signal remains unexplained in the strict sense. The lesson from the WOW signal is that anomalous signals exist in the radio sky, and that confirming them requires either repeated detection or detection by multiple independent instruments. Future SETI infrastructure, particularly the Square Kilometre Array, a planned array of radio telescopes covering a total collecting area of 1 square kilometre, capable of unprecedented sensitivity and sky coverage, would provide the ability to rapidly confirm or deny any anomalous detection across a global network of telescopes. Let us now talk about the specific question of what artificial intelligence might contribute to the Fermi Paradox search, about how the same technologies raising concerns about existential risk are also transforming our ability to search for signals of other civilizations. Machine learning algorithms have already been applied to SETI data with interesting results. In 2017, a machine learning algorithm applied to data from the Breakthrough Listen program identified 72 new fast radio bursts in archival data from the Arecibo telescope, a type of astrophysical phenomenon not predicted to be produced by extraterrestrial intelligence, but illustrating the power of AI to extract signals from noisy data that human analysts had missed. The application of AI to technosignature searches is more direct. The sky survey data that the Vera Rubin Observatory will generate, approximately 20 terabytes per night over its 10-year operational lifetime, is too large for human astronomers to comprehensively examine. Machine learning classifiers trained to identify anomalous light curves, unusual spectral signatures, or patterns inconsistent with known astrophysical phenomena, could flag candidates for human follow-up at a rate and scale impossible with manual analysis. The question of what pattern we are actually looking for, what the signature of artificial technology would look like in astronomical data, is itself a productive research program. Theoretical predictions of what megastructures would look like to our instruments, what waste heat profiles would be distinctive, what atmospheric technosignatures are uniquely biological or technological, these predictions constrain what AI classifiers should be trained to find. The irony that AI might solve the Fermi paradox, that the technology raising concerns about a civilizational great filter might be the instrument by which we discover whether other civilizations pass through it, is not lost on researchers in the field. Let us now talk about the specific observation that has come to be called the Fermi Paradox's most recent empirical surprise, the discovery that interstellar objects pass through our solar system. In 2017, astronomers detected an object travelling through our solar system on a hyperbolic trajectory, a path that indicated it had come from outside the solar system rather than from the Oort cloud or Kuiper belt. They named it Oumuamua, a Hawaiian word meaning approximately messenger from afar arriving first. It was the first confirmed interstellar object detected in our solar system. Oumuamua was unusual in several respects. Its shape was inferred from its rotation and light curve to be highly elongated, roughly cigar-shaped or pancake-shaped, with dimensions perhaps 400 by 40 by 40 meters. This is unlike any known solar system object. It exhibited an anomalous acceleration, not fully explained by solar radiation pressure, given its estimated mass. It was accelerating away from the Sun faster than gravity alone would predict. Harvard astronomer Avi Loeb attracted significant attention with a paper suggesting that Oumuamua might be an artificial object, perhaps a light sail or solar sail of extraterrestrial manufacture. The anomalous acceleration, the unusual shape, and the absence of the cometary outgassing that would normally explain non-gravitational accelerations in solar system objects all suggested to Loeb that Oumuamua defied conventional explanation, and that the extraterrestrial technology hypothesis deserved consideration. The mainstream astronomical community largely rejected this interpretation. More conventional explanations, hydrogen outgassing invisible to our instruments, a nitrogen ice fragment from an exoplanet's Pluto analog region, a collection of loosely bound dust, were proposed and remain the leading explanations. In 2019, a second interstellar object was detected, Borisov, which behaved entirely normally, showing cometary outgassing and having a conventional comet-like appearance. This demonstrated that interstellar objects pass through our solar system, and most are ordinary. The Oumuamua incident is relevant to the Fermi Paradox in two ways. First, it demonstrates that interstellar objects, potentially including artificial objects, could pass through our solar system without us detecting them, unless they are large enough or come close enough to us. The question of how many interstellar objects pass through the solar system that we miss entirely is relevant to the question of whether ET probes could be in our vicinity without our knowing. Second, it illustrates the difficulty of interpreting anomalous objects. The difference between genuinely extraordinary and merely poorly understood is not always obvious in real time. The Legacy Survey of Space and Time, conducted by the Vera Rubin Observatory, should detect many more interstellar objects in coming years. Statistical analysis of their properties, their shapes, their trajectories, their compositions, will help determine whether Oumuamua was genuinely anomalous or merely the first of many similarly unusual objects from the interstellar medium. Let us now talk about what is sometimes called the simulation hypothesis in the context of the Fermi Paradox, not as a mystical claim, but as a serious philosophical argument with specific implications for the paradox. Philosopher Nick Bostrom articulated the simulation argument in 2003. The argument is a trilemma. Either almost all civilizations at our level of development go extinct before becoming capable of running detailed simulations of their own history, or almost all such civilizations that survive choose not to run such simulations, or we are almost certainly living in a computer simulation run by some more advanced civilization. If either of the first two conditions holds, most civilizations are destroyed or abstain from simulation. If neither holds, then the number of simulated minds vastly exceeds the number of non-simulated minds, and the probability of being in a simulation approaches 1. The simulation hypothesis is relevant to the Fermi Paradox because it provides a potential resolution. If we are in a simulation, the simulated universe need not obey the same rules as the base reality in which the simulation is running. There is no requirement that simulated civilizations produce detectable signals that are visible to base reality observers. The simulation might be set up to produce exactly the apparent emptiness we observe. The Fermi paradox is not paradoxical in a simulation, because the apparent silence is a feature of the simulated environment rather than evidence about the base reality. Whether this is a satisfying resolution depends on one's philosophical commitments. For those who accept Bostrom's simulation argument as a legitimate inference, the resolution is coherent. For those who reject the argument as unscientific or unfalsifiable, it is not productive. The simulation hypothesis also connects interestingly to the AI risk version of the Great Filter. If advanced civilizations typically create simulations of their own pasts, and if they also typically develop AI that destroys them, then the universe might be populated primarily by simulations of civilizations that no longer exist in base reality. Cosmic archaeological remnants rendered in digital form. This is deeply speculative, but it illustrates the range of conceptual space that serious thinkers have explored in attempting to explain why the universe appears empty. Let us now talk about one of the most productive recent framings for thinking about the Fermi Paradox, what researchers have begun calling the Mesa hypothesis, or the grabby aliens hypothesis, developed by economist Robin Hanson along with James Miller, Marin Soljacic, and Adam Jermin. The grabby aliens model makes the Fermi paradox quantitative in a new way. It begins with the observation that if advanced civilizations expand through space at some fraction of the speed of light, they would eventually produce detectable signatures, regions of space where the background radiation or the distribution of matter has been visibly modified by intelligence. We observe no such regions. The model asks, given that we observe no such regions, what does this tell us about how common civilizations are and how fast they expand? The model finds that the silence places a concrete constraint. Either civilizations are extremely rare, fewer than approximately 1 per cubic gigaparsec volume, or they expand at very slow fractions of the speed of light, or some combination of both. The grabby aliens model essentially translates the qualitative Fermi paradox into quantitative bounds on civilizational parameters. One of the most striking results of the model is that if civilizations are not extraordinarily rare, if they arise with reasonable frequency, and if they expand at modest fractions of the speed of light, then we should expect the universe to be well on its way to being colonized by now. The silence places a hard upper bound. If we are not already inside the light cone of some expanding civilization, if no civilization's expansion front has yet reached our region of space, it imposes constraints on how common civilizations can be. The model also makes a prediction about when we should expect to encounter a grabby civilization, a civilization whose expansion has reached our region. If civilizations exist at a frequency consistent with the observed silence, we should expect to be contacted or engulfed by an expanding civilization within the next few 100 million to few billion years. Not tomorrow, not for millions of years, but within a cosmologically recognizable timescale. This is itself a disturbing prediction. The reason the model predicts contact within a few billion years is that if civilizations existed at higher frequencies, we would already have encountered them. The fact that we have not encountered one yet, combined with the hypothesis that we will eventually encounter one, places us in a specific early window of cosmic history. Let us now talk about the connection between the Fermi paradox and existential risk, about why the same research community that studies the paradox also works on risks from artificial intelligence, nuclear weapons, engineered pathogens, and other potential catastrophes. The connection is direct and logical. If the Great Filter is ahead of us, if the silence of the cosmos is explained by civilizations consistently failing at some point after reaching our level of technology, then identifying and surviving that filter is the most important practical problem our civilization faces. The existential risk research community centred at institutions like the Future of Humanity Institute at Oxford, the Machine Intelligence Research Institute, the Centre for Human-Compatible Artificial Intelligence, and the Cambridge Centre for the Study of Existential Risk, takes the Fermi Paradox seriously as one of the empirical inputs to the question of how dangerous our current trajectory is. The argument is not that any specific technology is the great filter. It is that the pattern of silence across the galaxy suggests that advanced civilizations rarely survive to become galaxy-spanning. If that pattern is real and not an artifact of our ignorance, then the forces leading to civilizational failure must be powerful, consistent, and operating at approximately our stage of development. Nick Bostrom's work on existential risk explicitly uses the Fermi Paradox as evidence. The fact that we observe no ancient advanced civilizations is consistent with the hypothesis that advanced civilizations are consistently destroyed. The destruction mechanism is unknown. It might be nuclear war, AI, engineered biology, something we have not yet invented. But the consistent absence of old civilizations across a galaxy old enough to have produced them is at least compatible with the claim that something destroys civilizations before they get old. The practical implication is that whatever is destroying civilizations is likely related to technology, since civilizations seem to fail after becoming technologically capable enough to produce detectable signatures, but before becoming galaxy-spanning. The window in which a civilization becomes detectable but has not yet become galaxy-spanning is precisely the window of technological development, the period when a civilization is powerful enough to make big mistakes but has not yet become stable and resilient enough to survive them. We are in that window right now. This is the disturbing, practical implication of the ahead of us great filter hypothesis. Let us now talk about what the most careful researchers in the field currently believe, about the state of expert opinion on which resolution of the Fermi paradox is most likely correct. There is no consensus. The researchers who have thought most carefully about this question disagree substantially with each other about which resolution is most plausible, but certain patterns in the disagreement are revealing. Among physicists and astronomers working on the empirical aspects, the exoplanet surveys, the SETI searches, the technosignature programs, the most common view is something like the following. The rare intelligence hypothesis remains viable. The quantitative work of Sandberg and colleagues showing that the observed silence is consistent with us being alone is taken seriously. The search for biosignatures in nearby exoplanet atmospheres is considered the most important near-term empirical test. The absence of any detection across the full range of SETI searches to date is genuinely informative, not merely a failure of technology. Among philosophers and social scientists working on the normative and policy implications, the existential risk researchers, the most common view emphasizes the great filter and takes seriously the possibility that the filter is ahead of us. This community tends to find the evidence for rare intelligence less persuasive than the evidence for civilizational fragility, in part because they observe in human history patterns of technological development that seem to systematically produce risks that outpace wisdom. The most intellectually honest position is that the uncertainty is genuine and large. We do not know whether we are alone or whether the galaxy is full of hiding or failed civilizations. We do not know whether the great filter is behind us or ahead of us. We do not know whether our civilization is unusual or typical. What we do know is that the question matters enormously. If we are alone, the implications are profound for how we value human civilization and how seriously we take its survival. If the Great Filter is ahead of us, the implications are urgent for how we approach AI development, biosecurity, nuclear proliferation, and every other technology that might represent the kind of threat that has reportedly destroyed every civilization before us. The Fermi Paradox is not merely a cosmological puzzle. It is possibly the most important question we have ever asked, and one that we are finally in a position to make genuine empirical progress on. Let us now talk about what concrete research programs over the next decade are most likely to advance our understanding, about what observations and experiments could most significantly change our probability estimates on the various hypotheses. The James Webb Space Telescope is already producing atmospheric spectra of exoplanets. Over the next decade, it will characterize the atmospheres of the most promising nearby habitable zone rocky planets, primarily in the TRAPPIST-1 system. If biosignatures are found, the rare intelligence hypothesis is powerfully constrained. Life is not rare in the cosmos. If no biosignatures are found across a dozen well-characterized, potentially habitable worlds, it is suggestive, though not conclusive, since absence of detection does not prove absence. The Vera Rubin Observatory, beginning full operations in the mid-2020s, will survey the entire accessible sky repeatedly over its 10-year operational lifetime, generating a dataset of light curves for billions of astronomical objects. Automated classification of this dataset, looking for anomalous variability inconsistent with known astrophysical sources, will be the most comprehensive technosignature search ever conducted. If megastructures or other large-scale engineering exist within a few thousand light-years, they will likely produce detectable anomalies in this dataset. The square-kilometre array, the planned International Radio Telescope network with total collecting area of 1 square kilometre, will, when operational in the late 2020s, provide radio SETI sensitivity orders of magnitude beyond what Arecibo or the Green Bank telescope provide. It will be able to detect the equivalent of our own radio leakage from nearby stars, a level of sensitivity that would detect a civilization broadcasting at our own level from tens of light years away. The search for life in our own solar system, Mars Sample Return, Europa Clipper, a potential Enceladus lander, will provide the most direct evidence about whether life originated independently at multiple locations in our cosmic neighborhood. An independent origin of life in our solar system would be an extraordinary constraint on the Great Filter. Each of these programs represents a concrete empirical test of specific hypotheses about why the universe appears empty. The coming decade may be the most important decade in the history of the Fermi Paradox, the period in which the puzzle begins to transform from philosophical to empirical, from abstract to testable. The silence has lasted 70 years as a formally recognized scientific puzzle. It may not last another 70. Let us talk about one of the most psychologically interesting aspects of the Fermi Paradox, the specific cognitive biases and reasoning errors that make it difficult for human beings to think clearly about the question of extraterrestrial intelligence. The first and most pervasive bias is what psychologists call the availability heuristic, the tendency to estimate the probability of something by how easily examples come to mind. When we think about intelligence in the universe, we think about ourselves. We think about human civilization, our cities, our technology, our art, our science. These things are vividly available to our imagination. The alternative, a universe utterly empty of intelligence except for us, is available to us intellectually, but not experientially. We have never experienced a universe without at least one intelligent species. This asymmetry in cognitive availability leads us to systematically underestimate the probability of rare intelligence. It is difficult to genuinely feel that we might be alone in an observable universe containing 2 trillion galaxies, each containing hundreds of billions of stars. The sheer scale of the cosmos makes solitude seem implausible in a way that has more to do with our cognitive limitations than with the mathematics. The second bias is the tendency to project our own values and behaviors onto hypothetical alien civilizations. The Fermi Paradox often assumes that any sufficiently advanced civilization would want to expand, would want to communicate, would produce waste heat visible across cosmic distances. But these are specifically human drives. A civilization that arose from a very different evolutionary history might have completely different motivations, might value stillness over expansion, information density over physical extent, concealment over communication. This is not merely a philosophical nicety. It has concrete implications for the paradox. If the assumption that civilizations want to expand is wrong, the paradox largely dissolves. The silence is not surprising if advanced civilizations do not expand. Our anthropocentric assumption that expansion is a universal drive may be one of the most significant errors in Fermi Paradox reasoning. The third bias is what philosophers call the reference class problem. When we ask whether intelligence is common, we are implicitly placing ourselves in some reference class, some set of possible observers, and asking what fraction of that reference class inhabits a universe with other intelligence. But which reference class do we belong to? Intelligent observers in general? Intelligent observers at our specific level of technological development? Intelligent observers in a universe with specific physical constants? The answer to the Fermi paradox can change dramatically depending on which reference class we choose, and there is no obvious principled way to select the correct one. The fourth bias is perhaps the most important for practical purposes, what might be called the urgency asymmetry. If the great filter is behind us and we are alone, there is no particular urgency to the situation. We can take our time to figure this out. If the great filter is ahead of us and most civilizations at our stage are destroyed, there is enormous urgency. The information is relevant to decisions we are making right now about AI development, biosecurity, nuclear policy, and other civilizational risks. The asymmetry in the practical consequences of the two scenarios creates a strong incentive to take the ahead of us filter seriously, even if the evidence is ambiguous. This urgency asymmetry does not make the ahead of us filter more likely to be correct. It does mean that the appropriate policy response to genuine uncertainty between the two possibilities looks quite different from the appropriate response to certainty. If there is even a 10% chance that the filter is ahead of us and that AI represents the filter, the expected cost of treating AI development seriously as an existential risk is very much lower than the expected cost of ignoring it. Let us now talk about a specific and underappreciated line of evidence relevant to the Fermi paradox: the observation that we seem to exist at a special time in cosmic history, and what that special timing implies. We exist approximately 13.8 billion years after the Big Bang, around a star approximately 4.6 billion years old, on a planet approximately 4.5 billion years old, as a civilization approximately 10,000 years old, with advanced technology approximately 200 years old. This situates us at a very specific point in cosmic time. the philosopher Brandon Carter introduced what he called the doomsday argument, a controversial reasoning that uses our apparent position in human history to estimate the probability of human extinction. The argument holds that if we are a typical human being, randomly selected from all humans who will ever live, and if we find ourselves at roughly this point in human history, approximately 100 billion humans born so far, then the total number of humans who will ever live is probably not vastly larger than 100 billion. Because if it were, if 100 trillion humans were going to be born in the future, we would be in the first 0.1% of all humans who ever lived, which would be statistically surprising for a random sample. The doomsday argument is deeply controversial and has been criticized on multiple grounds, principally that the selection of a reference class for typical human is problematic. But the underlying logic, that our position in temporal sequences is evidence about the length of those sequences, is more defensible than its applications, and has influenced subsequent thinking about civilizational timescales. Applied to the Fermi Paradox, this kind of reasoning produces an interesting constraint. If intelligence is common in the universe, we might ask why we find ourselves among the early civilizations, why our civilization appears to be at an early stage in the history of intelligence, rather than at a late stage when most civilizations that will ever exist already exist. Various answers have been proposed. We might be early because intelligence is genuinely rare and we are among the first. We might be early because the universe produces intelligence at a constant rate across cosmic time, and we are no more or less typical than any other epoch. We might find ourselves early because later civilizations are destroyed, because the filter is ahead of us, and most civilizations that would exist in the future will not exist because they will be destroyed. This temporal positioning argument does not resolve the paradox, but it adds another dimension to the discussion. The question of where we are in the history of cosmic intelligence is related to, but distinct from, the question of whether other intelligence currently exists. Let us now talk about the long game hypothesis, a resolution of the Fermi paradox that has received relatively little attention, but that some researchers find compelling. The long game hypothesis holds that advanced civilizations are not absent from the galaxy, they exist and they are interacting with the galaxy, but that we do not recognize their presence because we are looking at the wrong timescales and the wrong scales of activity. Consider the following analogy. Imagine bacteria living in a petri dish. The petri dish exists in a laboratory where humans are conducting experiments. The humans are present, are affecting the petri dish, are monitoring its contents. But from the perspective of the bacteria, the laboratory is empty. The humans are present at spatial and temporal scales utterly invisible to bacterial perception. The bacteria cannot see the humans, cannot detect their signals, cannot recognize their structures, because the bacteria are adapted to perceive things at bacterial scales. The long game hypothesis holds that we might be in an analogous position. Advanced civilizations might be operating at scales, either much larger or much smaller than we search, that our current instruments are not designed to detect. They might be operating on timescales of millions of years, within which our entire technological civilization is a single unresolved moment. They might have transformed the physics of their environment in ways that produce no signature visible to our current instruments. This is not a falsifiable hypothesis in its general form. There is always some scale or some time scale at which we have not searched. But it is not completely without empirical content. Specific versions of the long game hypothesis make specific predictions about what signatures should be present in data we already have. The search for evidence of stellar engineering modifications to stellar evolution that would extend the lifetime of stars, harvesting of stellar energy at the Dyson sphere level, the redistribution of stellar mass, is a concrete technosignature search motivated by the long game hypothesis. If ancient civilizations have been reshaping their stellar environments for billions of years, those reshapings should produce statistical anomalies in the distribution and properties of stars detectable in large astronomical surveys. The Gaia satellite has produced the most comprehensive catalogue of stellar positions, motions, and properties ever assembled, containing data for approximately 1.8 billion stars. Statistical analysis of this catalogue for anomalies inconsistent with stellar evolution models, but consistent with large-scale stellar engineering, is a legitimate research program that is beginning to be pursued. Let us now talk about the most philosophically profound version of the Fermi Paradox, the version that considers not just whether intelligence exists elsewhere, but what the answer means for the nature of the universe itself. The physicist Lee Smolin has argued that universes that produce intelligence might be special in a cosmological sense, that the existence of observers capable of understanding physical laws places constraints on those laws that have explanatory power. The anthropic principle, in its strongest form, holds that the universe must be structured so as to produce intelligence, that a universe incapable of producing intelligence would be somehow incomplete or contradictory. If this view is correct, the Fermi Paradox has a very different character. The question is not why a universe capable of producing intelligence produced so little of it, but what role intelligence plays in the structure of reality at the deepest level. Some physicists have suggested that quantum mechanics requires observers, that the wave function collapses only through observation, and that a universe without observers would be, in some sense, indeterminate. If intelligence is necessary for physical reality to be determinate, a deeply controversial view held by some interpretations of quantum mechanics, then the question of how common intelligence is becomes connected to the deepest questions in physics. This is far from the mainstream. Most physicists regard the observer dependence of quantum mechanics as a feature of the formalism rather than a feature of ontology. Quantum states do not literally require conscious observers to collapse, merely interactions with any macroscopic system. But the connection between the Fermi Paradox and the foundations of physics has attracted serious thinkers and is not obviously without content. At a less exotic level, the question of whether intelligence has a special role in the universe's long-term future is relevant to how we think about the stakes of the Fermi Paradox. The physicist and philosopher David Deutsch has argued that the creation of knowledge, including scientific knowledge, is the most important process in the universe, the one that most distinguishes the long-term future of the universe from its past. In this view, the absence of intelligence in the cosmos would represent a failure of the universe to develop one of its most extraordinary capacities. The stakes of the Fermi Paradox are not merely about our own survival. They're about whether the universe's capacity for self-understanding realizes itself or is cut short. Let us now talk about the specific implications of the Fermi Paradox for how we think about the search for life within our own solar system, and why the question of life on Mars or Europa is not merely interesting but potentially transformative for how we understand the paradox. The discovery of independent life in our own solar system, life that originated separately from Earth life, would be one of the most consequential scientific discoveries in human history for the Fermi Paradox specifically. Here is why. If life evolved independently twice in one solar system, the probability of life evolving in a given solar system must be much higher than 1 in 1. It is high enough that 2 independent origins occurred in a single system. This would strongly suggest that life is common throughout the galaxy. Billions of stars in the Milky Way with habitable planets, almost all of them with some form of life. The Great Filter cannot be at the origin of simple life, if life originates so readily. This would push the Great Filter to a later stage. Either the transition from simple to complex life, from prokaryote to eukaryote, from single cell to multicell, from simple animal to intelligence, is extremely improbable. Or intelligence is common, but civilizations are consistently destroyed. Both of these alternatives have different implications for optimism versus pessimism about our situation. If the filter is the transition from simple to complex life, the Cambrian explosion as a near impossible event, we might be genuinely rare and valuable as a complex life form, even in a universe full of simple life. If the filter is civilizational destruction, we are approaching it now. The Mars Sample Return mission, planned for the early 2030s by a collaboration between NASA and ESA, will return samples from Mars that may contain preserved evidence of past life, if life existed there. The analysis of those samples will be one of the most significant scientific events of the 21st century, specifically because of its implications for the Fermi Paradox. If the samples show evidence of past life on Mars, or evidence that Mars had all the chemical prerequisites for life, but no life developed, both results are informative. Life found would push the filter later. Life not found, despite suitable conditions, would be consistent with the filter being at or before the origin of life. Europa Clipper, launched in October 2024, will conduct detailed flybys of Europa and characterize its ocean, its ice shell, and its potential for habitability. It will not directly search for life. That would require a lander or a probe that penetrates the ice. But it will determine whether Europa's ocean has the chemistry and energy sources that life requires. This information will constrain models of the probability of life there and inform the design of future missions. Each of these solar system missions is therefore not merely interesting planetary science, it is Fermi Paradox research. The answer to, is there life on Mars or Europa, directly constrains which resolution of the Fermi Paradox is correct. Let us now talk about the specific and rather disturbing mathematics of the ahead of us Great Filter scenario, about what it would actually mean for the history of the galaxy if most civilizations are consistently destroyed. If the Great Filter is ahead of us, and if it operates at approximately our level of technological development, destroying civilizations before they become capable of interstellar colonization, then the galaxy has been experiencing a repeating pattern for billions of years. Intelligence arises, civilizations develop, they reach the threshold of technological capability. They are destroyed. The cycle repeats. The galaxy is littered with the ruins of civilizations that never expanded beyond their home systems. This has concrete astronomical implications. A civilization destroyed before expanding to other star systems would leave evidence on its home world and potentially on nearby worlds. Atmospheric modifications, surface chemistry changes, the spectral signatures of industrial activity, followed by their absence. An advanced SETI program might find these ghost signatures, worlds that show evidence of past technological activity now gone silent. This kind of search, sometimes called the search for technosignatures of dead civilizations, is beginning to be taken seriously as a research program. The spectral signatures of certain industrial pollutants persist in planetary atmospheres for thousands to tens of thousands of years after the industrial civilization producing them is gone. If a civilization was destroyed 100,000 years ago, its atmospheric pollution might still be detectable today. The mathematics of how many such ghost civilizations should exist, given various assumptions about the frequency of intelligence and the probability of surviving the filter, can be calculated. If civilizations are destroyed at a rate consistent with the silence we observe, and if the filter operates at approximately our technological level, then there should be hundreds to thousands of ghost civilizations within a few thousand light-years of Earth. Planets whose atmospheres still bear the chemical traces of civilizations that no longer exist. Searching for these ghost signatures, using the atmospheric characterization capabilities of JWST and future telescopes applied to nearby potentially habitable exoplanets, is a concrete research program that could test the ahead-of-us filter hypothesis. If we find numerous ghost signatures, worlds that show evidence of industrial activity followed by silence, it would be one of the most disturbing findings in the history of science. It would suggest that the filter is real, that it is consistent, and that we are approaching it. If we find no ghost signatures, either because no civilizations exist to leave them, or because we are the first at our level of development, it would constrain the frequency of civilizational emergence and the timing of the filter. Let us now talk about what has been called the intelligence explosion singularity as a Fermi Paradox solution, not merely as an existential risk, but as a specific astrophysically observable phenomenon. If civilizations consistently develop artificial superintelligence, and if that transition results not in destruction, but in a fundamental transformation of the civilization's goals and behavior, a transition from biological expansion-seeking intelligence to machine intelligence with radically different motivations, then the galaxy might be full of ancient superintelligences operating in ways that produce no detectable signature to our current instruments. The astronomer Stephen Webb, in his book If the Universe is Teeming with Aliens, Where is Everybody?, considered this scenario. A superintelligence might conclude that the optimal use of available resources is not physical expansion, but computation, specifically the most efficient possible computation, which might involve cooling matter to near absolute zero to take advantage of the thermodynamics of computation in a cold environment. A civilization pursuing maximum computation would want to wait, to allow the universe to cool as it expands, and would therefore become progressively less active and less detectable over cosmic time. This produces a specific prediction. Ancient superintelligences should not be visible as active, expanding civilizations. They should be quiet, cold, computationally intense, and invisible to instruments looking for the signatures of biological civilizations like radio broadcasts or thermal waste heat. The silence of the cosmos in the wavelengths we search is consistent with this hypothesis. But these same superintelligences would not be invisible to all possible observations. A sufficiently cold, dense, computationally intense region of space would have a distinctive gravitational signature and might affect the distribution of matter around it. Searches for anomalous, compact, massive objects, not black holes or neutron stars, but something else, dense, computationally intensive structures, could, in principle, detect these entities. This is entirely speculative. We do not know whether advanced computation motivates sufficiently advanced intelligence, whether near-zero temperature computation is theoretically optimal, or whether such entities could be distinguished from astrophysical objects with current instruments. But it represents the kind of concrete observational prediction that makes a speculative hypothesis scientifically useful. Let us now talk about what the Fermi Paradox tells us about the nature of scientific uncertainty at its most fundamental, about the specific epistemic situation in which science finds itself when confronted with a question whose answer determines the broadest context of everything else we study. Science is most comfortable with questions that can be tested against data from multiple independent experiments, where wrong hypotheses can be decisively ruled out and correct ones accumulate confirmatory evidence. The Fermi Paradox defies this framework in specific ways. We have one data point, our own civilization, from which we are trying to draw conclusions about a universal distribution. We are searching for something whose absence from our current observations is consistent with multiple incompatible hypotheses. We are reasoning about entities and processes operating at scales of time and space that dwarf anything we have direct experience with. The philosopher of science Karl Popper argued that the hallmark of a scientific hypothesis is falsifiability, the possibility of being proven wrong by an observation. The Fermi Paradox discussion includes many hypotheses that are difficult or impossible to falsify individually. The hypothesis that civilizations hide deliberately can be maintained regardless of what we observe. The hypothesis that we are in a simulation can be maintained regardless of any astronomical observation. The hypothesis that the Great Filter is at some future stage can be maintained unless and until our civilization survives to that stage. This does not mean the Fermi Paradox is unscientific. It means that progress on the paradox requires a different methodology, not the clean falsification of individual hypotheses, but the accumulation of evidence that progressively constrains the probability distribution over possible explanations. Each SETI null result rules out some region of parameter space. Each biosignature, detected or not detected, shifts the probability distribution. Each exoplanet characterized adds to the statistical picture. The question becomes more tractable even if never decisively resolved. The analogy is to cosmology in the early 20th century. The question of what the universe is, how large it is, how old it is, whether it is static or expanding, these questions seemed, in 1910, to be beyond scientific resolution. They turned out to be tractable through the combination of improved instruments, clever theoretical reasoning, and the willingness to follow evidence wherever it led, even when it contradicted prior beliefs. The Fermi Paradox may be at a similar stage, appearing intractable from within our current instrumental and theoretical framework, but accessible to a future framework we are building the foundations of today. The Square Kilometre Array, the Vera Rubin Observatory, the Habitable Worlds Observatory, the James Webb Space Telescope, the Extremely Large Telescope. Each of these represents a new capability that adds to the framework. The development of astrobiology as a rigorous scientific discipline, the maturation of the theory of biosignatures, the application of artificial intelligence to large astronomical data sets, each represents a theoretical and methodological advance. We are building the instruments and the frameworks that may allow the Fermi Paradox to be resolved not by philosophical argument, but by observation. What we find will determine not just the answer to an interesting cosmological question, but the context within which all of human civilization understands itself and its place in the universe. This is why the Fermi Paradox matters, not as a puzzle to be clever about, but as a question whose answer, whatever it turns out to be, will be among the most important things our species has ever learned. In the summer of 1950, Enrico Fermi asked a simple question over lunch. Where is everybody? 75 years later, we still do not have a definitive answer. But we know far more than Fermi did, and what we know has made the question simultaneously more tractable and more disturbing. We know that planets are common. Essentially, every star in the Milky Way has planets. Earth-sized planets in habitable zones of sun-like stars number in the billions in our galaxy alone. The universe is full of places where the preconditions for life are met. This was not known in 1950. It is known now, and it makes the silence more rather than less puzzling. Because the more places life could exist, the more surprising it is that we detect nothing. We know that our searches have become vastly more sensitive. The Breakthrough Listen initiative, the most comprehensive SETI program ever conducted, has surveyed millions of stellar systems with instruments orders of magnitude more sensitive than anything available to Fermi. It has found nothing. The radio sky is silent. The infrared sky shows no Dyson spheres. The optical sky shows no laser beacons. Nothing in any wavelength we have searched, across any timescale we have monitored, from any direction we have looked, has shown the unmistakable signature of another technological civilization. We know that the mathematics are sobering. The oldest stars in the galaxy are 9 billion years older than the Sun. Any civilization that began expanding at even 1% of the speed of light 1 billion years ago could have reached our corner of the galaxy millions of years ago. The timescales available dwarf any reasonable estimate of the time needed for galactic colonization. If expansion-minded civilizations exist, they should already be here. They are not, and we know, though this knowledge is newer and more uncertain, that the silence is consistent with us being alone. The work of Sandberg, Drexler and Ord showed that when we take seriously the full range of scientific uncertainty about the relevant parameters, the expected number of civilizations is not confidently large. It is broadly distributed. The silence is not paradoxical if the probabilities of life and intelligence at each step are small enough that one example in the observable universe is roughly what should be expected. These are the things we know. What we do not know, what remains genuinely, deeply uncertain, is which of these framings is correct. Are we alone? Possibly. The mathematics allow it. The silence is consistent with it. A universe of 2 trillion galaxies, each containing hundreds of billions of stars, 13.8 billion years of cosmic time, and exactly one place that produced observers capable of asking the question. That would be an extraordinary fact. It would also place on us a responsibility without precedent in human history or in the history of life on Earth. We would be the universe's only known means of understanding itself. Every choice we make about how to organize our civilization, how to develop our technology, whether to survive the coming centuries, would carry a weight that cannot be described in ordinary human terms. Is the great filter behind us? We may have already survived something extraordinarily improbable: the origin of life, the development of eukaryotic cells, the emergence of multicellular animals, the evolution of intelligence. Each of these steps may have been a near impossibility. If so, we are rare, not by accident, but by a series of improbable events that almost never reach their conclusion. The silence is not a warning, it is a measure of our rarity. Is the great filter ahead of us? The silence may be telling us something about our future rather than our past. Most civilizations that reach our level of development may not survive what comes next. Artificial intelligence that escapes alignment. engineered pathogens of catastrophic reach, nuclear war, technologies we have not yet invented that prove impossible to use safely. The galaxy may be littered with the ruins of civilizations that never passed through what we are approaching, and we may be approaching it now without knowing what it is. We do not know which of these is true. The honest answer, the scientifically defensible answer, is that the question remains open. But it is not forever open. The coming decades will bring more information. The James Webb Space Telescope will characterize the atmospheres of nearby potentially habitable planets. The Vera Rubin Observatory will survey the entire sky for anomalous phenomena that do not fit any known astrophysical explanation. The Square Kilometre Array will search the radio sky with sensitivity never achieved before. Mars Sample Return may tell us whether life arose twice in our solar system. Europa Clipper will tell us whether Europa's ocean has the chemistry that life requires. Each of these observations will shift the probability distribution. Each will tell us something about where the great filter lies, behind us or ahead of us, at the origin of life, or at the emergence of intelligence, or at the development of technology. The paradox that seemed purely philosophical in 1950 is becoming empirical. We are building the instruments that will constrain the answer. And the answer matters beyond anything we usually mean by scientific importance. If we discover life nearby, microbial life on Mars, chemical signatures of biology in the ocean of Europa, atmospheric biosignatures on a TRAPPIST-1 planet, it means the origin of life is not the great filter. It means life is common. And it means the filter, whatever it is, operates later. It means something destroys civilizations after they emerge, and we are approaching that something. If we discover that the nearby potentially habitable worlds are sterile, beautiful and warm and wet and entirely empty of life, it means life is rare. The filter is at or before the origin of life. We pass through it. We are alone, or nearly alone. And that aloneness is its own kind of answer. A universe of almost infinite extent and almost infinite duration, with almost nothing in it capable of understanding any of it, except us. Either answer is astonishing. Either answer changes everything about how we understand our situation. The question Fermi asked over lunch in 1950 was not really a question about aliens. It was a question about the nature of intelligence in the universe, about the fate of civilizations that develop technology, about whether consciousness and understanding are rare or common features of a cosmos that has been running its processes for 13.8 billion years. It is the deepest question we have ever asked with scientific instruments in our hands. And for the first time in the 75 years since Fermi asked it, we have the instruments to begin, genuinely begin, not merely speculate, to answer it. The sky is listening. We are listening back. What we hear, or do not hear, in the coming decades will tell us something fundamental about what we are and what we are likely to become. The silence continues, for now.